This will continue our discussion of Chapter 42 on elementary particles. And here we're going to look at what is called the Standard Model of Elementary Particles, section 42.2. Well, we just discovered in the last section that there were two groups of particles. They're the strongly interacting and they're the ones that have no strong interactions. Of the strong interactions, we have fermions. Incidentally, the strong interacting particles are called hadrons, and these are called, and they can be either fermions, which means that they're baryons, or they can be bosons, which means that they have a spin of 0, 1, 2, 3. These are half integral spin, in which case it means that they are mesons. If they don't have strong interactions, they can be fermions, or they can be another kind of particle called a gauge particle. We didn't discuss these last time. These are particles that mediate the forces between particles. These are mesons. I should put it here. Mesons. Did that wrong. Bosons. And these bosons that have no strong interactions are called gauge particles. Now, I didn't mention these in the last section, but this is, for example, the photon, the graviton. This mediates electromagnetic theory. This mediates the gravitational force, and we have some other particles that can also be strongly interacting. A gluon, which holds the quarks together. We're going to learn what the quarks are. And these fermions, there's 6 of these, you recall. There's the electron, the muon, and the tau, the neutrino for the electron, the neutrino for the muon, and the neutrino for the tau. And these 6 are called leptons. This nomenclature can be pretty confusing, so remember again, we have strongly interacting particles, which are called hadrons. They're divided up into spin 1/2, 3/2, and so forth, which are fermions, and therefore those are called baryons. If they have a spin of 0, 1, 2, or 3, they're called bosons, and if they're strongly interacting, they're called mesons. But I can also have fermions, spin 1/2, that don't have the strong interactions, and those are called the leptons. And there are only 6 of those, whereas there are hundreds of these. And I can have a boson, which is not strongly interacting, and these would be the gauge particles, like the photon and the graviton and the gluon. So what we want to address now is, we just have, 3 or 4 of these, and we have 6 of these, plus their antiparticles, but we have hundreds of these. Can these be considered as being made up of other particles? And the answer is yes. We discovered in the late 60s, there was a model of this called the unitary symmetry model, or SU3, that became expanded to SU4, then SU5, then SU6. And we finally discovered that this model is based on the fact that there are, making up all of these particles, 6 particles called quarks. And these quarks all have half integer spin, they're fermions, and they have the strong interactions, so they're hadrons. And they build up all of these particles, both the fermions, which are baryons, and the bosons, which are mesons. This new classification of particles means that this 6 particles here turns out to have a strong resemblance in their interactions and so forth, and symmetries, a parallel between these 6 and these 6 here that are leptons and don't have the strong interactions. What are these quarks? Well, physicists have named these very strangely. The up quark, the down quark, the strange quark, the charm quark, the top quark, and the bottom quark, called U, D, S, C, T, and B. And all of these 6 particles right here, these quarks, build up every single one of these hundreds of fermions and bosons. They all have half-integral spin, they all have strong interactions, and these quarks are bound together extremely tightly using what are called gluons. These gluons hold these quarks together. And in fact, we can look at how some of these are made up. The patterns that these baryons and mesons are made up of fit into a pattern in a mathematical theory called group theory. And these patterns in group theory are very interesting in the way that they're made up. And that's how they were originally discovered, by the group theory properties, which shows certain patterns of these, kind of like the periodic table of Mendeleev in the 1800s. So the Mendeleev's work in the late 1800s, around 1880, where he found new elements by looking at the patterns of the elements that existed, and he could actually predict their masses and their properties, was repeated again in the late 60s and early 70s with the understanding of these quarks and the patterns that they made up for the baryons and the mesons, and we were able to predict new models, new particles. For example, if we look at this model, the proton is actually made up of a down quark and 2 up quarks. So a proton is actually equal to a down quark, an up quark, and an up quark bound together extremely tightly with an exchange of gluons among them. The neutron is made up of a down quark and a down quark and an up quark. A pion, which is a meson that jumps back and forth between the proton and the neutron, is actually made up of a down quark and an anti-particle for an up quark. This has a spin of half, this has a spin of half, and those 2 half spins are in the opposite direction, giving this a spin of 0. These have spins of 1/2 each, and they will have 2 of their spins will be anti-aligned in the opposite direction, canceling out, and the spin for the rest of the particle comes from the other one. It turns out, though, that something very strange about all of these quarks is that they have fractional charge. Of either 1/3 of the electronic charge or 2/3. That can be positive or negative of the electric charge. And they have to be put together in a particular way that is rather complex. Now what we have on the whole that we have learned at this point is that there's 6 leptons right here, and there's 6 quarks right here, and these patterns match very, very closely in their interactions that they have of the four different types of forces. The quarks are held together by gluons. The electromagnetic force is responsible for the photon is responsible for that. The graviton for the gravitational force, and another particle called the W particle or the Z particle is responsible for the weak force that jumps back and forth. So all in all, this gives us our model for the elementary particles. Most of you would think at this point, wait, this is too many. I have 6 leptons and I have the antiparticles. So that's 12. I have 6 quarks and they're antiparticles. That's 12 more. That's 24 particles. Here's the 25, 26, 27, and the Z particle and the W particle, 28, 29. This is too many. I have about 30 particles. And these are considered elementary within the Standard Model. So what people have tried to do now is do something very different. They have looked at a possible theory involving strings, where these strings are the fundamental things, either closed or open. And these strings are extremely small and live and vibrate in other dimensions other than our three spatial dimensions and our one-time dimension. And this is a very complex theory that is very exciting because it tries to build up all the elementary particles from these two types of strings that oscillate and various types of membranes that oscillate in a higher dimensional universe. But these things are incredibly small, much, much smaller than anything we had ever envisioned before. Whether or not this is true or not, we don't know. We're still waiting for some type of prediction or understanding or proof, and we don't see that on the horizon right now. But much work is going on looking at these strings and seeing if string theory could possibly give us an answer on the most fundamental level of what these particles are made up of. At some point, we hope to get to the place where we can say everything is made up of these and these are not made up of anything else. There's some kind of fundamental thing in the universe, like a string, for example, or some one type of phenomena out of which its manifestation over several different ways could lead to all of the different other things that we see. That's our hope.